The account begins with a description of an extensive sequence of marine observations in which autonomous underwater vehicles gather data across a vast range of depths and temperatures in an effort to map biological movement patterns that have remained poorly quantified for decades, and the material presented here focuses on one particular anomaly recorded during a deep water survey operation in a sector of the ocean previously considered comparatively stable in terms of large fauna transit and current behavior, and the drone responsible for the recording was equipped with high-resolution sonar LiDAR, hydrodynamic sensors, and a reinforced optical system capable of capturing movement in low light and extreme turbidity. And despite these capabilities, the footage that emerged challenged known marine biological speed thresholds by revealing a shadow-like form traversing the sensor field at a velocity that exceeded the limits established for any documented predatory species, and subsequent analysis re-examined the hydrodynamic resistance factors encountered at depth, the physiological constraints on muscle fiber performance in vertebrate and invertebrate marine organisms, and the known limitations of propulsion strategies used by apex predators such as lamnid, sharks, sailfish, and orca populations, and none of these models aligned with the characteristics observed in the recording, prompting an expansive inquiry into potential mechanical, geological, or unknown biological explanations. And as the drone descended during the initial leg of the survey, its telemetry noted a stable pressure gradient, with minimal particulate interference, allowing for exceptionally clear acoustic readings. And this clarity made the later anomaly even more striking, because the absence of disruptive variables removed many common error sources, and the shadow emerged as a brief distortion recorded across 3 separate sensor arrays simultaneously, which suggested that it was not a glitch or artifact caused by equipment failure. And in reviewing the raw time-stamped data, the moment of crest contact appeared as a sudden attenuation of ambient light captured across multiple spectral bands, and this attenuation was too coherent to be random and presented as a uniform absorption signature rather than a reflection or refraction effect, implying the presence of a motile object with low albedo properties, moving at a velocity that surpassed the known energy output to feasible for marine creatures at that depth. And while the recording lacked anatomical detail, it showed an elongated form that produced no cavitation trails, which contradicted established hydrodynamic expectations, since any substantial mass moving at such speed through water should generate turbulent wake patterns. Yet the sensors captured no such turbulence, only a subtle pressure indentation in surrounding water columns that dissipated unusually quickly, and the lack of wake in combination with the recorded acceleration curve indicated a mode of movement not reliant on muscular propulsion or conventional fin-based locomotion. And further complicating analysis was the manner in which electromagnetic readings dipped at the exact moment the shadow intersected with the drone's observation field, suggesting that the phenomenon interacted with or emitted a form of energy previously undocumented in marine mobility studies. And as the dataset expanded through forensic review teams evaluated comparative anomalies recorded in entirely different oceanic sectors over the past 30 years. And while none matched the magnitude of this event, several contained faint signatures hinting at similar rapid transitory movement previously dismissed as noise in the data. And these historical re-examinations implied that the ocean may host rare events of extreme velocity movement that evade detection due to their brevity, their unpredictability, and the limitations of older people sensor technology. And building upon these findings, researchers developed models hypothesizing that certain deep water regions might contain transient physical conditions that allow for momentary reductions in hydrodynamic drag, possibly created by intersecting thermoclines or mineral-rich upwellings that alter fluid density on microscales. Though these models remain highly speculative and do not fully explain the consistent shape and uniform absorption signature recorded by the drone. And as the discussion progressed, new simulation software was implemented to stress test biomechanically impossible locomotion patterns, and these simulations predicted that an organism utilizing an advanced form of magnetohydrodynamic propulsion could, in theory, achieve the velocities recorded, but would require anatomical adaptations currently unknown in Earth-based marine biology, including conductive TIS, use highly efficient energy conversion systems, and structural reinforcement. capable of withstanding immense shear forces. And yet, even these hypothetical organisms would be expected to produce wake disturbances, which the recorded anomaly lacked in parallel to the biological theory's geological explanations were considered, including the possibility of rapidly shifting mineral deposits or gas plumes, creating transient shadows in sonar or optical readings, but these failed to account for the synchronized cross-sensor detection, the electromagnetic disturbance, and the acceleration curve, which pointed to intentional directed movement rather than passive drift or geological collapse, and the transformed unknown. Understanding of what constitutes valid anomalies expanded the investigative mandate of the research project, leading to further deep dive deployments, each outfitted with upgraded sensor arrays capable of recording at higher frame rates in 25, both acoustic and optical spectrums. And these follow-up missions did not initially produce comparable results, which highlighted the rarity and unpredictability of the event, though they did reveal subtle patterns in deep water current interactions that may provide contextual clues for future detection. And the review of the drone's path during the encounter indicates that it passed through an area characterized by a multi-layer density inversion, a condition known to cause unusual acoustic bending. Yet this too could not account for the unanimity of the data across independent sensors and the notion that the shadow represented an undiscovered marine preda. Tor remains controversial because any organism capable of such speed would necessitate an ecological niche entirely, unlike those observed in known food webs, raising questions regarding its sustenance, energy requirements, reproduction, habitat stability, and some researchers have posited the existence of extremely low visibility, deep scattering layers composed of cryptic fauna, adapted to near-zero light conditions that evade conventional detection methods by absorbing expolancid rather than reflecting incoming light. Yet again, the magnitude of the event challenges even these expanded frameworks and contributes to a re-evaluation of how biological scale and energy efficiency function under long-term high pressure. Evolutionary conditions, and beyond biological speculation, the event has catalyzed advancements in underwater sensor methodology, shifting focus toward capturing multidimensional transient distortions rather than identifiable anatomy, because the absence of recognizable features in the recording highlights the need for tools designed not to classify known life, but to detect unknown modes of interaction between mass energy and fluid environments, and the very idea that the decnoning oceans may contain mechanisms or entities capable of momentary velocities exceeding apex predators disrupts long-standing assumptions regarding stability in deep-water ecosystems, and suggests that unexplored hydrodynamic principles may shape life in ways not yet understood. And these insights further support interdisciplinary research, tying together marine physics, evolutionary biology, fluid dynamics, and geophysical anomaly mapping in an attempt to construct a cohesive explanation for the singular shadow, whose existence challenges conventional boundaries across all related fields. And the implications extend beyond academic curiosity because understanding such phenomena could inform future engineering strategies for efficient underwater transport and reconnaissance technology. By studying what little is known about this event, one may reverse engineer theories about how drag, reduction, and energy conversion might be achieved under extreme pressure regimes, and such engineering aspirations mirror the historical pattern in which biological observations inspire technological innovation. Yet in this case, the observed behavior appears so radically detached from any documented organism that its utility as a model remains purely theoretical until more encounters occur. And as research teams continue to scrutinize the raw data frame by frame, it becomes evident that the anomaly's shadow-like presentation is not a product of insufficient imaging, but a true characteristic of an object or phenomenon optimized for minimal reflectivity, which could imply evolutionary pressure favoring detection. Avoidance on a scale far surpassing that of known, camouflaged, or deep-dwelling species, and the possibility arises that what was recorded represents not a stable organism, but a transitional state of matter or energy producing a coherent within a fluid medium while not obeying typical biological constraints. And if such a possibility is entertained, the event must be viewed through the lens of physical rather than biological taxonomy. And this reframing may be necessary because the metrics defining mass acceleration, absorption, and electromagnetic disturbance do not align with terrestrial biology, and as such, researchers are increasingly open to frameworks that account for non-traditional interactions between energy fields and dense fluid environments, especially in regions of the planet historically underexplored due to technological limitations. And in this context, the drone footage serves as a pivotal data point, signaling a frontier of marine science wherein the unknown may not take the form of recognizable organisms, but rather transient high-speed anomalies whose existence challenges the foundational CA. Assumptions upon which marine ecology and deep-sea physics have long relied as ongoing examination expands the scope of inquiry surrounding the recorded underwater anomaly. Researchers shift focus toward the surrounding environmental metadata captured during the mission to determine whether subtle variations in temperature, salinity, or chemical composition might have created a transient medium capable of facilitating unorthodox movement speeds, and early reviews suggest the presence of a faint chemical stratification, possibly generated by slow seepage from deep crustal fissures known to release mineral-rich fluids, yet these detected concentrations were minimal and insufficient to account for the near frictionless trajectory implied by the drone's sensor readings, and this insufficiency reinforces the notion that the anomaly either possessed intrinsic properties enabling it to bypass conventional hydrodynamic resistance, or occupied a microenvironment of unknown composition, generated instantaneously at the moment of transit, which dissipated too rapidly for calibration instruments to measure, and deeper layers of analysis explore the possibility that quantum-level interactions could theoretically reduce drag under extreme pressure conditions, though such theories remain speculative due to the challenge of reconciling large-scale biological motion with quantum mechanical principles. And while such combinations appear improbable within established frameworks, similar improbabilities have historically preceded paradigm shifts, especially in fields studying systems as complex and extreme as deep ocean. Environments and companion investigations examine potential acoustic anomalies and frequencies outside standard monitoring ranges, attempting to detect whether any subsonic precursors occurred immediately before the shadow passed through the starring observation field, and although no confirmed precursors were identified, a peculiar harmonic resonance appeared 3 seconds prior to the event, too faint to warrant classification, yet sufficiently unusual to warrant future instrument refinement, specifically targeting detection of low-frequency distortions that may serve as indicators of high-velocity movement in dense mediums. And this resonance may signal a rapid compression or displacement of water in advance of the flashed anomaly, though confirming this hypothesis would require additional datasets featuring similar events, and in exploring available archives, researchers examined decades of satellite imagery data, searching for unusual micropulses or distortions in sea surface height that could correlate with deep underwater rapid movement. But these efforts yield mostly noise because the immense depth at which such anomalies occur typically prevents any detectable surface expression. However, a few ambiguous altimetry spikes in remote sectors of oceanic basins present tantalizing but inconclusive evidence that similar events may have transpired previously, going unnoticed due to the lack of synchronous deep water instrumentation, and the research initiative gradually expands into a cross-institutional collaboration, incorporating experts in fluid mechanics, geophysical modeling, and bioluminescence theory to evaluate whether any established natural systems might even remotely parallel the characteristics observed, and perhaps the closest analogy can be drawn from certain gelatinous organisms whose bodies exhibit near complete transparency and minimal reflective surfaces, enabling them to avoid detection across optical spectrums, yet their locomotion remains orders of magnitude slower than the velocity recorded in the anomaly, and their structural fragility directly opposes the kind of extreme force tolerance required to sustain such speed. So these analogies serve only as reminders of how far the recorded event lies outside known biological parameters, and attention then shifts to rare reports of deep scattering layer disruptions documented by submarines during classified missions decades earlier, some of which described abrupt mass displacement of organisms without identifiable source. As though the documentation is sparse and lacks the multimodal sensor sophistication available in the present event, and while these historical accounts do not directly support the presence of a high-speed shadow-like phenomenon, they suggest an environment in which unexplained large-scale movement may occur and subsequently fade into the abyss without leaving lasting traceable effects. And confronted with this accumulating yet insufficient body of evidence, researchers propose the possibility that the anomaly may represent a type of non-continuous presence appearing only under specific environmental conditions, perhaps linked to deep-sea thermal pulses generated by mantle plume interactions or by sudden, compressive shifts along subsea tectonic boundaries. And under such conditions, unique physical properties might emerge long enough for an unknown entity or energy mass to manifest movement patterns impossible under stable conditions, though. This theory remains contentious due to the precision and uniformity observed in the recorded shadow, which appears more controlled than reactive and more directional than a byproduct of tectonic forces, and emerging from these debates is an often alternative perspective that reclassifies the shadow not as an entity, but as a signature of transition between states of matter, wherein the darkened form represents the optical artifact of something shifting between physical conditions not typically stable in the oceanic environment. And this perspective hypothesizes that the recorded velocity was not movement through space in the traditional sense, but rather the side effect of a rapid phase shift that only appeared to traverse distance due to the drone's perceptual limitations relative to the phenomenon's temporal dynamics. And this interpretation, although unconventional, helps reconcile the absence of hydrodynamic wake, the transient electromagnetic dip, and the lack of anatomical features, by positing that the anomaly may not behave like localized mass, but instead resembles a moving boundary between two coexisting energetic states. If such a boundary moved at the moment recorded, it could leave behind a shadow-like impression on optical sensors without engaging in the physical interactions expected from conventional marine organisms. And this hypothesis also aligns with the fast dissipation time observed in the pressure traces as a transitional boundary would not create sustained turbulence, but instead generate a passing distortion that rapidly reverts to equilibrium. And the implications of this model are far-reaching because it reframes the event as a potential geophysical or even atmospheric intrusion into the marine environment, albeit one that operates at depth levels far beyond typical exchange zones between Earth systems. And following this conceptual shift, research teams initiate computational fluid dynamic simulations incorporating hypothetical, low-density, high-inertia boundaries, interacting with pressurized seawater, and early results demonstrate that under extremely narrow conditions, such boundaries could appear as dark moving forms across visual sensors without producing cavitation trails, though the required energy to product these boundaries exceeds known natural sources, unless emergent, deep crustal processes or unknown suboceanic phenomena contribute additional energy inputs. And alongside these simulations, an increasing focus is placed on mapping the electromagnetic dip recorded during the event, which stands out as one of the most quantifiable clues in the dataset. And this dip did not align with standard interference patterns nor with known biological bioelectric signatures, instead presenting as a smooth suppression across a broad band of frequencies lasting only a fraction of a second, yet sufficiently distinct to indicate active interaction rather than passive absorption. And if an unknown energetic boundary were passing through the region, it may have temporarily displaced existing electromagnetic fields, causing the suppression, and such displacement could explain the shadow-like nature of the event, while also fitting the profile of a non-material transition. However, further validation would require multiple observations, which remain unavailable. And the rarity of such events suggests that the conditions enabling them may be exceedingly localized and ephemeral, perhaps requiring narrow thermal gradients, specific mineral saturations, and finely tuned pressure fields to create a permissive environment. And this dependency may account for the absence of similar recordings in adjacent survey zones, even when using identical equipment and methodological parameters. And the constant appearance of dead ends in biological, geological, and mechanical explanations reinforces the need for new interpretive framework. KS aimed at understanding transient deep ocean anomalies as aspects of broader planetary physics rather than isolated occurrences, and this interdisciplinary reframing prompts reevaluation of long-held assumptions about deep ocean uniformity, revealing that what was once considered a stable environment may in fact harbor rare energetic interactions, occurring beyond the resolution of traditional instruments. And the drone's recording therefore stands as the first high fidelity capture of a phenomenon that may have occurred countless times before, undetected due to its speed, its near invisibility, and the absence of wake or reflective surfaces that would expose its presence. And as these analyses continue, researchers examine the possibility that the anomaly may represent an emergent system arising from nonlinear fluid interactions, wherein sudden convergences of temperature and salinity gradients produce coherent moving shadows that mimic the behavior of mass even though they possess none. And while similar effects have been observed on far smaller scales in laboratory conditions, no known mechanism allows such phenomena to reach the size, scope, or velocity recorded in the Planck. Drones capture, yet the theoretical possibility demonstrates how little is understood about mesoscale fluid behavior under extreme pressure regimes, and further simulations explore whether deep ocean vortices could generate transient void spaces of reduced density, allowing for rapid displacement of water that might resemble high-velocity movement. But these vortices would require rotational forces orders of magnitude higher than anything found in natural environments, and furthermore, the shape observed in the recording displayed linear motion inconsistent with vortex dynamics, which typically produce spiraling or rotational signatures easily identifiable in subscribe acoustic datasets. And as more explanations are considered and excluded, the anomaly assumes increasing importance as a potential precursor to a new class of deep water events, defined not by biological function or geophysical structure, but by unconventional motion signatures that defy established classification systems. And this perspective reframes the event as an essential data point in understanding unexplored marine dynamics, suggesting that oceans may contain poorly understood interactions between water pressure, mineral-saturated, microcurrents, electromagnetic fields, and possibly unknown forms of energy transfer, capable of manifesting as fleeting high-speed shadows and expanding this perspective. Researchers begin conceptualizing new drone models equipped not merely with cameras and sonar, but with multidimensional sensing arrays capable of detecting subtle shifts in gravitational microgradients, high-frequency electromagnetic daughter oscillations, and rapid density fluctuations that might precede or accompany similar events. And the development of such technology marks an essential evolution in deep-sea monitoring by shifting emphasis from identifying discrete organisms to capturing transient energy states and fluid distortions that signal the presence of phenomena without stable material forms, and the potential for such sensors to reveal a hidden layer of deep ocean physics is profound, offering insights into a realm where motion, light, and pressure interact in ways not previously measured or theorized. And, in reflecting on the magnitude of the anomaly, researchers acknowledge that the event challenges fundamental definitions of what constitutes presence, motion, and interaction in underwater environments. And these foundational challenges extend beyond oceanography, influencing emergent fields studying the boundaries between fluid mechanics, energy transfer and geodynamics, and the recorded shadow thus operates not merely as a mystery, but as an anchor around which future scientific exploration may evolve, pushing the boundaries of understanding into pretension. Territories once thought purely speculative, and yet now partly illuminated by the impossible speed and perfect silence of a form that moved without wake, without anatomy, and without precedent, leaving only a momentary mark on the instruments, built to measure a world far better understood than it truly is. As research initiatives expand further into the analysis of the anomaly, a new focus emerges regarding the energy budget necessary to produce the observed velocity to electromagnetic disturbance. And this focus raises profound questions about whether known, biological, or geological systems possess the capacity to generate such rapid and coherent manifestations of motion, and as teams calculate the required energy expenditure, they conclude that for a mass even equivalent to a medium-sized marine organism, to achieve the recorded acceleration without producing cavitation, it would require an efficiency exceeding the theoretical maximums of biological muscle function by several orders of magnitude. and this discrepancy reinforces the hypothesis that the recorded phenomenon may not adhere to classical mechanical principles as applied to biological mass, and instead may rely on unknown processes, enabling movement unconstrained by conventional drag forces. And such processes could theoretically involve localized water displacement fields that temporarily reconfigured the surrounding fluid environment, allowing the anomalous shadow to move through a corridor of reduced resistance. Though whether such a corridor could be generated naturally remains an open question, and additional scrutiny is directed at the faint thermal gradients captured immediately after the anomaly passed, which showed a subtle cooling effect contradicting expected patterns, wherein friction or compression would typically generate heat, and the cooling effect suggests either the absorption of thermal energy by the phenomenon itself or a transient inversion of microthermal structures, possibly caused by rapid redistribution of fluid density fields in the anomaly's wake. And while slight, effect remained consistent across multiple sensor logs, suggesting that it was not a calibration error, but a genuine environmental response to the event. And further adding complexity is the observation that the area in which the anomaly Prakiden occurred has historically presented unusually stable oceanographic conditions with minimal thermal fluctuation and remarkably consistent salinity metrics, making the sudden localized cooling even more unusual, and researchers theorize that the anomaly may have induced a momentary reorganization of molecular structures within the water, increasing order within the fluid matrix, which in turn could reduce local temperature though. Such an ordered state would dissipate quickly, restoring equilibrium, and this theoretical increase in molecular order aligns loosely with known phenomena in high-pressure physics, where matter can behave unpredictably under extreme compression. But parallels remain tenuous due to the complexity and scale of open ocean conditions compared to laboratory environments. And in contemplating these possibilities, researchers turn to the deep ocean's role as a reservoir for geophysical energy, where subtle variations in pressure and temperature coexist with mineral-saturated plumes, generating dynamic microscale interactions still poorly understood. And within these frameworks, some propose that the anomaly may represent a rare convergence of these microscale interactions, amplified by naturally occurring resonant oscillations, capable of structuring fluid environments in ways that allow otherwise impossible behavior to manifest, and though unproven. These resonant models gain traction as they provide a potential mechanism for the creation of transient low drag fields enabling ultrafast movement. And to evaluate these ideas, large-scale simulations are conducted replicating conditions of extreme depth, mineral saturation, microcurrent interaction, and high-pressure oscillation fields, attempting to determine whether combinations of these variables could create translation corridors through which a coherent shadow-like form might propagate without experiencing typical hydrodynamic restraints. And initial simulations produce partial analogs, showing that under extremely narrow parameters, wave interference patterns can briefly clear a linear channel of altered density, but these channels last microseconds and are far smaller than what the anomaly would require. And thus, while simulations hint at intriguing possibilities, they fall short of this, explaining the sustained trajectory observed in the drone footage. And this persistent gap between simulation and observation drives researchers to expand data collection zones, seeking subtle environmental precursors such as shifts in osmosis, mineral plume composition, rhythmic pressure pulses, or unexplained electromagnetic drifts that might precede events of this nature. And new instrument deployments begin mapping seabed fissures, fault lines, and hydrothermal vent systems in the Plos's Rend region, aiming to determine whether slow geological processes could be producing intermittent conditions favorable for the emergence of such phenomena. Yet, despite extensive mapping efforts, no direct correlation is found suggesting either the conditions are more subtle than measurable, or the phenomenon arises from mechanisms entirely separate from local geology. And in parallel, research into marine biochemistry investigates whether unknown biochemical agents could reduce, drag, or distort optical readings by creating refractive gradients in surrounding water. And although certain microorganisms produce compounds capable of altering surface tension, may have been documented affecting hydrodynamic drag at depth, nor have any been observed acting on scales consistent with the recorded event. And this absence strengthens the argument that the anomaly represents neither biological camouflage nor chemical interference, but a process functioning at a level beyond the scope of known organic interactions and turning again to the electromagnetic dip. Researchers plot the waveform against known interference profiles and discover that the suppression resembles neither natural nor artificial signatures, instead forming a smooth curve reminiscent of theoretical models describing field collapse around objects transitioning between different energy states. And if the anomaly were undergoing such a transition while passing through the detection zone, this could account for the uniform darkening across optical and sonar arrays as electromagnetic fields momentarily reorganize, creating an absorption-dominant signature rather than reflective or refractive ones. And this interpretation continues to grow more plausible when considering how the anomaly produced no measurable bioluminescent response from surrounding plankton populations, which typically react when disturbed by rapid movement or pressure shifts. And yet, these organisms showed no deviation, suggesting that the anomaly may have displaced water without generating turbulence or tactile pressure fronts, thus passing silently and invisibly through an environment highly sensitive to disturbance. And this silent motion stands in stark contrast to all known marine predators, whose rapid movements inevitably produce wake turbulence or sonic signatures detectable across multiple sensory modalities. And the anomaly's ability to traverse water without triggering these responses lends support to models in which it does not move through water, but instead moves with or inside a transient boundary layer separating two energetic states. And if such a boundary layer were sufficiently coherent, it could hypothetically slide through seawater like a phase interface encountering minimal resistance and leaving minimal disturbance behind. And the rarity of such conditions may explain why similar events have escaped detection for so long, only appearing under narrow thresholds of pressure, chemical composition, and electromagnetic balance, and attention then shifts to the long-term implications of such phenomena, particularly in regard to ocean circulation dynamics, heat storage patterns, and deep-sea energy exchange, and if unknown transient events periodically introduce high-velocity boundary shifts within water columns. This could influence localized mixing patterns, or even trigger micro-oscillations in stratified layers, contributing to long-term variability currently attributed to unknown causes. And thus, the anomaly may represent not an isolated incident, but part of a larger system of deep ocean processes that subtly modulate planetary energy distribution, though such processes have remained beyond detection until the systemile. The present, due to their fleeting nature and low reflectivity, and investigating this possibility requires new modes of measurement, leading to the conceptual development of persistent nunger sensors capable of remaining at depth for years, continuously tracking electromagnetic variance, thermal anomalies, density inversions, and microacoustic disturbances at resolutions several magnitudes greater than current systems. Such an array would form a deep ocean observatory network, capable of capturing the precursors or signatures of similar events, thereby enabling pattern recognition and temporal prediction. Though the financial and technical requirements of such an endeavor remain substantial, and while planning progresses, researchers analyze the drone's raw footage frame by frame again and again, measuring pixel-level distortions and sonar phase interference with increasingly precise computational techniques, and these analyses reveal previously unnoticed microshifts in the direction of light attenuation, suggesting that the shadow may have possessed internal gradation rather than uniform opacity, indicating a structured, though undefined interior composition, and this structure appears fractal in distribution, implying a nested organization of sublimits arranged in a pattern more reminiscent of energy distributions than biological anatomy. And considering these findings, scientists propose a radical interpretation wherein the anomaly is neither organism nor solid boundary, but rather a coherent volumetric distortion sustained by an internal energy gradient, enabling it to maintain shape while internal energy crasted, traversing fluid environments at anomalous speeds. And if such gradients can manifest in natural settings, they may represent a physical phenomenon previously unknown, offering in-sig DHTS into unrecognized aspects of energy organization under extreme conditions. And such gradients may arise spontaneously in deep-water environments when mineral-saturated plumes interact with high-pressure electromagnetic fields produced by tectonic stress, frictional heating, or mantle-derived charge differentials, though the exact mechanisms remain speculative, and increasingly the shadow appears less like a creature and more like a manifestation of physics occurring on a scale rarely observable. And the drone recording stands not as a glimpse of an undiscovered species, but as evidence of a rare moment when environmental forces align to produce a visible trace of deeper planetary processes unfolding silently in the abyss. And this interpretation shifts the significance of the footage from biological anomaly to physical revelation, indicating that Earth's oceans may host intermittent expressions of energetic transitions that rarely intersect with human observation and which remain undocumented solely because the technology capable of perceiving them has only recently become available, and the realization that such phenomena may exist challenges fundamental assumptions about deep ocean uniformity and stability, urging a reconsideration of how energy is stored, transferred, and expressed in the planet's most remote environments. And this reconsideration opens the possibility that the oceans contain transient states of matter or energy, whose interactions produce observable movement without mass-driven locomotion, reshaping the conceptual boundaries of fluid dynamics, geophysics, and marine science simultaneously. And thus, the shadow captured by the underwater drone stands as a rare bridge between observed reality and theoretical possibility, a data point suggesting that the deep sea hosts events beyond the scope of established science waiting to be understood through technologies and frameworks still in their infancy. As inquiry into the anomaly deepens, research teams broaden their analytical framework to incorporate principles from plasma physics, materials science, and nonlinear fluid mechanics, recognizing that the event may represent an intersection of disciplines traditionally treated as separate. And through this multidisciplinary lens, investigators begin modeling the anomaly, not as a biological entity, but as a coherent structure formed through environmental energy gradients, capable of manifesting distinct shape and velocity within a dense fluid medium. And these models explore whether sudden shifts in mineral ionization, electromagnetic flux, or pressure stratification might produce vortical sheets of energy with enough coherence to adopt transient geometric boundaries, observable as shadow-like forms across optical and sonar systems. And this line of investigation gains traction due to a subtle pattern detected in ultra-high-frequency acoustic readings, where a brief resonance spike occurs at the leading and trailing edges of the anomaly, suggesting that the form had definable front and rear boundaries despite lacking anatomical features, and the existence of such boundaries implies an organized internal structure, perhaps resembling stratified layers of energy-dense eddy, or pressure, potential interacting with the surrounding seawater in a manner comparable to a lens passing through a fluid, altering its refractive characteristics. And if this analogy holds, the anomaly may not have been an object, but, rather, a moving interface between regions of different energetic states, producing a silhouette effect on the drones, cameras, and sensors, and further complicating interpretation is the discovery of microscopic particulates suspended in the water sample. Retrieved hours after the event, these particulates displayed irregular lattice formations, not commonly associated with naturally occurring sediment or biological debris. And though their presence cannot be definitively linked to the anomaly, their unusual geometry suggests exposure to intense but fleeting forces capable of altering crystalline structures without raising water temperature significantly, and such forces could be consistent with theoretical models involving rapid reorganization of local electromagnetic fields or pressure wave collapses. And if such reorganization occurred during the anomaly's passage, it might explain the faint thermal dip, electromagnetic suppression, and shadow-like optical signature recorded simultaneously. And as these possibilities gain scientific attention, the nature of the deep ocean itself comes under re-examination, prompting the hypothesis that the sea may host intermittent physical states, analogous to atmospheric phenomena such as sprites or ball lightning, which require specific yet fleeting conditions to become visible and measurable. And in this framework, the anomaly could represent a marine analog to transient luminous events, albeit expressed through pressure density and electromagnetic modulation, rather than visible charge emissions. And while such comparisons remain speculative, they offer a first conceptual foothold for understanding how a structured, high-velocity phenomenon could arise without biological or mechanical origin. And parallel to these theoretical efforts, researchers conduct high-pressure laboratory experiments, simulating extreme seafloor conditions using pressurized tanks infused with mineral-saturated fluids subjected to oscillating electromagnetic fields. And while these experiments fail to reproduce the anomaly's behavior, they do produce small, scale distortions in the water that resemble simplified versions of the shadow-like forms recorded during the event, though at far lower speeds and durations, and these distortions appear to form when microcavitation sites collapse simultaneously across a narrow corridor, producing a temporary tunnel of altered refractive index within the water. And although the laboratory distortions lack the coherence and momentum observed in the anomaly, they demonstrate that fluid mediums under high pressure and electromagnetic variability can produce structured transitory features, challenging assumptions about how mass and motion interact at depth. And following this discovery, researchers revisit decades-old, unexplained submarine sensor recordings stored in classified archives, some of which contain brief anomalies previously dismissed as sensor noise. Yet a small subset display attenuation patterns, faintly resembling those recorded by the drone, suggesting that such events, while rare, may not be unique. And this retrospective analysis reveals that many of these historical recordings occurred in regions characterized by slow tectonic drift, high mineral flux, supporting the hypothesis that geological processes may play a role in enabling the conditions necessary for anomaly formation. And with these correlations emerging, scientists develop a model proposing that migrating zones of subcrustal stress may generate electromagnetic pulses through piezoelectric interactions within mineral-dense rock. And these pulses could propagate into surrounding water columns, where they temporarily reorganize fluid density fields, creating corridors or sheets of altered hydrodynamic resistance capable of sustaining high-velocity propagation of energy structured in a shadow-like formation. And if correct, the anomaly represents not an organism, but the expression of a geological energy discharge distributing itself through the ocean in patterns visible only under the right conditions. And from this vantage point, the ocean becomes a dynamic medium through which planetary energy occasionally travels in structured forms not yet cataloged within physics. And this perspective reframes the deep sea as an active participant in planetary energy exchange, rather than a passive reservoir of water heat and organic matter. And as this idea gains scientific support, new attention focuses on the anomaly's extreme velocity, which far outstrips the movement of any known marine waveform, including solitons, internal waves, or Hermohaline pulses. And because classical hydrodynamic equations do not permit such motion without generating destructive turbulence, researchers turn to quantum fluid models, which allow for the possibility of coherent, non-turbulent displacement under specific energy conditions, though such behavior has only been observed in supercooled laboratory environments, not in naturally occurring seawater. And yet the recorded anomaly shows several hallmarks consistent with these quantum models, such as minimal wake formation, uniform absorption, signature, and rapid dissipation, leaving researchers to contemplate whether localized quantum-like behavior could manifest spontaneously within deep ocean conditions driven by geological energy influx. And while no current theory adequately explains how such behavior could arise at large scales without cryogenic temperatures, the possibility underscores how little is understood about the relationship between pressure, temperature, salinity, and electromagnetic fields in extreme marine environments. And this uncertainty fuels a new era of exploration, wherein oceanographers, physicists, and geologists collaborate to develop hybrid theories merging aspects of classical and quantum physics to describe deep ocean anomalies, and new predictive algorithms are constructed to detect minute precursors such as microelectromagnetic fluctuations, harmonic pressure spikes, and mineral ionization, layers that may precede similar events. And early versions of these algorithms retroactively identify several near misses in archived datasets, subtle environmental alignments that would have produced anomalies but apparently did not, suggesting that the conditions necessary for formation are extraordinarily precise and that even slight deviations can prevent manifestation entirely. And this razor threshold of occurrence explains both the rarity of such phenomena and the difficulty of reproducing them experimentally or predicting their future appearance. And as understanding deepens, the anomaly evolves from an unexplained outlier into a potential indicator of rare planetary processes, offering insight into the transfer of geophysical energy into the hydrosphere. And such processes may operate continuously, but only under specific alignments do they become visible as structured shadow-like forms. Moving through the ocean at extraordinary speed, and in contemplating the planetary significance of these events, researchers evaluate whether similar phenomena could influence long-term oceanic behavior, including mixing patterns, nutrient transport, and deep water formation cycles. And though impacts appear negligible on human timescales, the cumulative effects over geological periods may be substantial, contributing to the evolution of ocean chemistry and thermal distribution in ways previously attributed solely to surface climate factors. And such a possibility hints at a hidden layer of Earth system dynamics, in which rare deep-sea events serve as pressure release mechanisms or energy transfer pathways, maintaining long-term equilibrium within the planet's complex interior and exterior systems. And if so, the recorded anomaly represents more than a scientific curiosity. It represents direct evidence of a regulatory mechanism embedded in Earth's natural processes, one that operates silently in the abyss, invisible until captured by modern instruments capable of perceiving its brief signature. And as the significance of this possibility becomes clear, international research initiatives plan new deep-sea expeditions targeting regions where tectonic, mechanical, electromagnetic, and mineralogical conditions mirror those present during the anomaly recording. And these missions aim to capture additional data, enabling comparative analysis crucial for validating or disproving emerging theories. And to support these efforts, new underwater drones are equipped with quantum-tuned magnetometers, hyperspectral imagers, and ultra-high-frequency sonar arrays designed to detect even the faintest shifts in density or energy state transitions. And these upgraded systems will allow researchers to observe anomalies not merely as shadows, but as full multi-dimensional events, enabling measurement of internal structure, propagation mechanics, and interaction with surrounding seawater at resolutions previously impossible. And with these developments, the anomaly becomes a cornerstone of a new scientific frontier, challenging assumptions, redefining boundaries, and revealing that the deep ocean, long regarded as Earth's least dynamic domain, may host some of the planet's most extraordinary energetic phenomena. And the space realization that such events exist, even if only rarely, forces a reconsideration of what motion means within a fluid medium, what energy means within a geophysical context, and what observation means within the constraints of human technology and perception. And thus the underwater drone's recording stands not only as evidence of a shadow that moved faster than any known predator, but as the first glimpse into a deeper, the realm of planetary behavior waiting to be mapped, measured, and understood. As analysis progresses and the anomaly becomes embedded within a broader context of planetary energy dynamics, researchers refine their understanding of the conditions under which such a phenomenon might manifest by compiling datasets from every known deep-sea expedition that recorded unexplained optical or acoustic distortions. And while most historical anomalies prove inconsistent with the event captured by the drone, a small subset displays faint signatures resembling attenuated versions of the same shadow-like movement, exhibiting similar electromagnetic suppression and local thermal dips, albeit far weaker, suggesting that the recorded shadow may represent an extreme expression of a class of events rather unexpressed than a singular occurrence. And this emerging classification allows scientists to construct probability maps, identifying regions most likely to exhibit transient structured motion based on underlying geological, mineralogical, and electromagnetic factors. And these maps reveal a curious pattern wherein anomaly-conducive regions align with slow-moving tectonic boundaries, characterized by high mineralization rates and irregular electromagnetic flux, implying that geological stress may play a direct role in enabling the conditions required for boundary formation capable of using shadow-like propagation through seawater. And in this context, the anomaly becomes a potential marker of geophysical restructuring events, functioning as transient manifestations of energy redistribution within Earth's lithosphere. Transmitted through the hydrosphere in forms not previously recognized by traditional instrumentation, and further study of mineral-rich seeps in the region reveals fluctuating ion distributions consistent with piezoelectric discharges that occur when crystalline minerals undergo stress deformation, suggesting that the ocean floor may periodically emit electromagnetic pulses strong enough to reorganize local water density fields, creating temporary corridors of reduced hydrodynamic resistance. And although these pulses are typically too weak or too brief to produce large-scale effects under certain rare alignments of pressure, temperature, and mineral concentration, they may amplify into structured energy fields capable of sustaining coherent movement at extreme velocities, and researchers begin to conceptualize these fields as hydrodynamic waveguides where energy, rather than matter, propagates through water in a form that appears shadow-like to optical instruments and capable of traversing long distances without dissipating. And if such waveguides can form naturally within Earth's oceans, they may serve as conduits for rapid energy transport, functioning as deep-sea equivalents of atmospheric jet streams, albeit composed not of moving fluid, but of propagating boundary states, whose movement is perceptible only when intersecting with sensor fields or objects C, capable of reflecting attenuation effects. And this conceptual shift explains why the anomaly exhibited a defined shape despite lacking mass, because the shape was not the outline of a physical body, but the spatial expression of a propagating body. Field interacting with the drone's optical and acoustic systems in a way that translated into a shadow-like signature, and scientists further explore whether such field propagation could account for the anomaly's acceleration curve, which exhibited near instantaneous transition between stationary and high-velocity states, something impossible for a biological organism, but characteristic of energy fields that propagate at the speed of their internal dynamics rather than through propulsion. And such behavior mirrors certain plasma structures observed in laboratory settings, where instabilities within electromagnetic fields produce coherent moving surfaces that appear to accelerate instantly without inertia. And if analogous processes can occur within seawater under deep pressure, they may produce natural plasma, like formations stabilized by mineral ion concentrations, which in turn behave as coherent shadow forms traveling through water with HO. Minimal interaction with the surrounding environment. And this line of reasoning leads researchers to reevaluate the role of dissolved minerals, metals, and salts as not merely passive chemical constituents, but as agents capable of supporting complex electrochemical behavior analogous to ionized gases in atmospheric plasma events. And such reevaluation highlights the possibility that Earth's oceans may contain overload oaked conditions conducive to low-energy plasma formation, stabilized by pressure and hydration shells, forming structures invisible to the naked eye, yet capable of interacting with optical and acoustic systems when organized into coherent geometries. And if the anomaly was such a structure, it may have formed spontaneously as a result of mineral saturation gradients interacting with underlying tectonic stress fields, creating a momentary plasma-like boundary that propagated rapidly before dissipating as internal energy equilibrium broke down. And this model gains traction, particularly because it accounts for the anomaly's lack of turbulence, electromagnetic dip, and shadow-like appearance, while also explaining its sudden disappearance and lack of residual disturbance. And while the idea of underwater plasma states challenges conventional thinking, researchers point to known examples such as sonoluminescence and electric discharges in spotty, supersaturated fluids, demonstrating that dense water environments can sustain exotic energetic states under the right conditions. And though these states have never been observed at the scale implied by the anomaly, the principle remains theoretically plausible, given sufficient pressure mineralization and electromagnetic stimulation. And in exploring deeper implications, scientists consider whether such plasma-like events might contribute to large-scale biogeochemical cycles. By altering mineral structures in the water, perhaps influencing nutrient distributions or catalyzing chemical reactions otherwise impossible under standard conditions, and such influence Hoff, subtle on individual scales, could accumulate over geological time, shaping aspects of ocean chemistry previously attributed to other mechanisms. And thus, The anomaly may represent not only a rare geophysical event, but a functional component of Earth's chemical evolution, albeit one that has remained hidden until recently due to the extreme conditions required for manifestation, and the realization that such events may exist inspires new efforts to create more. Sensitive deep-sea monitoring arrays capable of detecting the full spectrum of energy interactions at depth, including ultra-low frequency, electromagnetic waves, nanoscale density fluctuations, and transient refractive shifts, all of which may serve as precursors or residual signatures of these boundary state formations. And these arrays seek to transform the deep ocean from a largely unobserved environment into a strongly instrumented domain where anomalies can be detected in real-time, enabling continuous monitoring of geophysical processes traditionally studied only through indirect surface-based measurements, and early simulations predict that if enough sensors are deployed, researchers may observe hundreds of microevents for every major anomaly of the type recorded by the drone. Though these microevents would likely be too small or too weak to produce visible shadow-like motion, they would nonetheless offer valuable insight into the dynamics that precede large-scale field propagation. And by cataloging these patterns, scientists could eventually predict when conditions are primed for the emergence of larger structured events, thereby providing opportunities to capture multiple recordings and refine theoretical models accordingly. And alongside these technological developments, mathematical modeling of the anomaly continues to evolve, with researchers adapting equations from magnetohydrodynamics and nonlinear wave theory to describe how energy boundaries might propagate through fluid mediums. And these models incorporate variables such as ion concentration, gradient pressure, anisotropy, electromagnetic flux alignment, seeking to reproduce the anomaly's observed velocity, shape, and attenuation profile. And while early models succeed in generating simulated structures that resemble the anomaly's silhouette, none yet achieve comparable velocity without violating energy conservation principles, prompting researchers to propose the existence of temporary energy borrowing from local fields analogous to how certain atmospheric phenomena briefly utilize surrounding charge distributions to accelerate propagation. And if similar energy borrowing mechanisms occur in seawater, they may temporarily lower the energetic cost of boundary propagation, enabling rapid motion without sustained local depletion, and this would explain why the anomaly's environmental impact was minimal, as such borrowing would be transient and highly localized, restoring equilibrium moments after dissipation. And in recognizing these dynamics, researchers also consider whether the anomaly reflects a broader category of planetary behavior, where an energy moves through Earth systems in structured packets that occasionally intersect with observational tools, creating rare glimpses into processes otherwise invisible to human perception. And such processes may occur across multiple environments, including the mantle crust, atmosphere, and oceans, unified by underlying physical principles, yet manifesting differently depending on medium composition, pressure, and temperature. And though these planetary scale interactions remain largely theoretical, the anomaly provides the strongest evidence yet that such processes may exist and may influence Earth's internal balance in ways not yet understood. And increasingly, the scientific community views the anomaly not as an isolated event, but as part of a hidden continuum of energy transformation, spanning geological, biological, and physical domains. And this continuum suggests that Earth systems interact more dynamically than previously believed with deep ocean environments, serving as conduits for energy exchange, capable of producing observable signatures when conditions align perfectly. And the rarity of such alignments explains why only one high-resolution recording exists, despite decades of exploration. Yet the existence of even one confirmed event validates the possibility of many more occurring undetected, underscoring the need for advanced instrumentation and sustained monitoring to reveal the true frequency and nature of such occurrences. And in assessing the broader implications, researchers consider how these phenomena might influence ocean evolution across geological timescales, potentially explaining unresolved anomalies in sedimentation rates, mineral distribution patterns, and long-term malgradients. And if deep ocean plasma-like boundaries periodically redistribute energy or alter mineral bonds, they could subtly shape seafloor chemistry over millions of years, contributing to cycles of mineral deposition and dissolution that influence marine ecosystems from the deepest trenches to continental shelves. And though such influences may appear negligible on human timescales, their cumulative effect could be profound, offering a revised understanding of how Earth maintains chemical and thermal equilibrium across its vast and varied components. And thus the anomaly emerges as a key observation, unlocking a deeper understanding of planetary processes, illuminating pathways of energy transformation long hidden within the abyss, and challenging researchers to expand the foundational principles of oceanography, geophysics, and fluid dynamics to encompass phenomena that transcend traditional classifications of matter, motion, and energy. And in this evolving scientific landscape, the underwater drone's recording becomes more than an isolated mystery. It becomes a catalyst, a data point that forces the reimagining of the ocean as a dynamic, energetic environment where rare but consequential events occasionally reveal the underlying complexity of Earth's internal workings. And with this realization, the pursuit of knowledge shifts from merely explaining a singular shadow to uncovering the unseen architecture of planetary behavior that produced it, and will continue to produce it, in forms yet to be observed as scientific momentum accelerates around the study of the anomaly research groups. Begin refining a new classification system to categorize deep ocean energetic events based on attributes such as electromagnetic suppression, thermal deviation, hydrodynamic disruption, attenuation geometry, and propagation velocity. And this classification system tentatively designates the drone-recorded event as a Type 3 structured boundary propagator, distinguished by its coherent silhouette, extreme speed, and lack of wake features. And this emerging taxonomy allows researchers to situate the anomaly within a hierarchy of related events, some of which have been detected only through partial data signatures in historical archives. And as this framework evolves, patterns begin to emerge indicating that researchers' Type 3 events may require a convergence of low-frequency tectonic vibration, electromagnetic flux drift, and mineral ion concentration thresholds that must be met simultaneously to enable formation of stable propagating boundaries, and these thresholds appear so narrow that even slight deviations in any parameter render formation impossible, explaining why the anomaly manifested only once during the research mission, despite days of continuous operation in the same region. And as models grow, increasingly precise researchers examine global datasets to identify regions where similar conditions might arise. And surprisingly, these regions correspond not only to known mineral-rich tectonic boundaries, but also to areas where unexplained anomalies in deep-sea conductivity and heat flow have been recorded in past decades, suggesting that such events may be one ingredient within a broader system of energy circulation that intermittently influences deep-water geophysics. And as the conceptual landscape expands, scientists begin analyzing the anomaly through the framework of energy coherency, a principle describing how distributed energy fields can briefly align into structured formations that exhibit properties not predictable from the behavior of individual components. And in the case of the anomaly, such coherency may arise from the synchronized oscillation of mineral ion concentrations, pressure fluctuations, and electromagnetic shifts, forming a stable boundary with internal phase alignment, enabling it to propagate rapidly without dispersing. And if this interpretation is correct, the anomaly represents not a single event, but a manifestation of a larger system of oscillatory interactions that occur across geological timescales. And the ability of such a boundary to move independently through seawater indicates that it may temporarily decouple from the energy sources that created it, functioning as a free propagating structure until stochastic instability causes its collapse. And this independence mirrors certain atmospheric wave structures, which once generated can travel long distances across the planet without continued forcing, though the deep ocean equivalent operates through far more complex interactions involving multidimensional energy fields shaped by immense pressure and mineral density. And as these analogies form, the next stage of research focuses on the anomaly's interaction with seawater itself, noting that its passage left no biochemical disruption among suspendae into organisms, implying that the boundary propagated not through displacement, but through refractive modulation, which modified how light and sound traveled through the region, creating the illusion of a physical shadow while leaving ambient conditions nearly unchanged. And this reveals the possibility that the anomaly exerted influence on the medium through which it traveled, not by pushing water aside, but by temporarily altering its physical properties akin to a phase lens. Shifting wave behavior around a traveling center, and such a mechanism aligns with theoretical predictions that high-coherence energy fields can create zones of modified refractive index without requiring mass leading to the shadow-like appearance recorded in the footage. And pushing this idea further, computational modeling suggests that the boundary's internal energy gradient may have temporarily altered water compressibility, enabling propagation with reduced drag, preventing the formation of cavitation bubbles, which typically accompany rapid underwater movement. And this lack of cavitation explains the near-silent acoustic profile captured alongside the anomaly, in stark contrast to biological locomotion, which inevitably produces turbulence and sound. And the intangible nature of the anomaly also aligns with observations of its near-perfect symmetry during the milliseconds it remained visible on high-frequency sensors. That is characteristic of energy-structured forms rather than living organisms, which inherently display irregularities due to biological motion and structural asymmetry. And researchers conclude that this symmetry, combined with the lack of wake and the electromagnetic dip, places the anomaly firmly outside the domain of biology and squarely within a category of energy-based propagating states not previously documented in natural marine environments. And as scientific confidence grows in this new interpretation, attention turns toward understanding the governing dynamics that allow such a boundary to maintain coherence over distance and at extreme velocity. And one hypothesis suggests that multiple resonance fields may align to produce a self-reinforcing envelope, stabilizing the boundary and preventing collapse, analogous to standing wave structures in physics, which maintain form through constant internal oscillation while moving energy across space. And for such a structure to exist underwater at extreme pressures, it would require a fine balance between mineral ion concentration, electromagnetic flux gradients, and thermal distributions, each contributing to the formation of a coherent envelope that can temporarily resist external perturbation and maintain its geometry long enough to be recorded. And while this remains theoretical, researchers recently developed microscale simulations demonstrating that under precise electromagnetic and ionic conditions, fluid pockets can exhibit quasi-stable wave envelope formations that shift light in ways similar to the attenuation observed during the wave anomaly. Although at microscopic scales and without significant velocity, and while these are far from replicating the phenomenon, they confirm the physical plausibility of energy envelope that's forming within dense mediums, challenging the assumption that only solid or biological structures can create defined moving shapes underwater. And as these breakthroughs accumulate, new investigative frontiers open, exploring the 25 possibility that deep ocean energetic boundary events may serve as indicators of large-scale tectonic transitions. And this idea arises from an unexpected correlation between the anomaly's timing and a subtle seismic tremor detected in the Poncev surrounding region hours after the event. And though the tremor was too faint to be felt or noticed without specialized equipment, its temporal proximity raises the possibility that the anomaly may represent an early stage or precursor, the signal of tectonic movement generated by interactions between mineralized crust and accumulating mechanical stress. And if energetic boundaries emerge during stress realignment events, this may provide a new method for predicting tectonic boundary shifts, particularly in remote subsea regions where traditional seismic equipment offers limited coverage. And the long-term implication is that anomaly detection networks could eventually serve as planetary monitoring systems, offering advanced warnings for geological activity that currently remains hidden within the ocean floor. And in exploring this possibility, researchers compare the anomaly's electromagnetic suppression signature to known data recorded near sub-oceanic fault lines, and this comparison reveals striking similarities, particularly in the smoothness of suppression curves, which resemble signatures detected during microfracture events where aerial stress redistributes electrical charge within rock layers. And under specific conditions, these electrical discharges may propagate outward into the water column, manifesting as coherent boundary structures. And while this correlation does not prove causation, it strongly suggests that energetic field formation in seawater may be tied to charge displacement events occurring deep within the crust. And if this link holds, the anomaly may represent a previously unknown interface between geological stress cycles and oceanic energy propagation, offering insight into how deep Earth processes interact with the hydrosphere and influence planetary equilibrium. And this insight widens the conceptual horizon, even further proposing that Earth's internal dynamics may periodically imprint themselves onto the ocean, not through heat or physical displacement, but through structured energy signatures revealed only under rare alignments of pressure, mineral concentration, and electromagnetic drift. And in this context, the deep sea becomes a vast resonant chamber through which geological energy occasionally organizes into coherent forms, producing ephemeral events visible only to highly sensitive instruments. And this understanding reframes the anomaly not as an outlier, but as one instance of a larger class of natural expressions through which the planet releases or redistributes internal energy. And if such expressions play a role in long-term geological regulation, they may influence processes ranging from crustal cooling rates to mantle convection patterns, though such implications remain speculative and require decades of additional research to validate. And as these questions accumulate, international scientific efforts intensify, aiming to establish a global network of deep-sea monitoring stations specifically designed to detect energetic boundary propagation, with the goal of constructing a chronicle of events across multiple oceans, providing a dataset robust enough to determine whether the anomaly represents a common yet elusive phenomenon or a rare environmental alignment unlikely to reoccur soon. And initial deployments include multi-vector electromagnetic arrays, hypersensitive acoustic refractors, and particle imaging velocimetry systems designed to capture minute refractive distortions even in minute, near-zero visibility environments. And early test results from prototype installations reveal several weak refractive disturbances consistent with Type 1 unstructured boundary fluctuations, suggesting that the ocean indeed hosts a spectrum of energy interactions previously overlooked due to insufficient instrumentation. And though none yet match the scale or speed of the Type 3 event recorded by the drone, these detections confirm that the deep sea contains complex energetic dynamics far richer than anticipated, and that with continued refinement, the full spectrum of boundary events may eventually be cataloged and understood. And as these developments unfold, scientists reflect on the broader significance of the anomaly, recognizing that the event challenges traditional boundaries between disciplines, illuminating the interconnected nature of geological, electromagnetic, chemical, fluid dynamic systems, which together create the possibility for phenomena that transcend current scientific categories. And the anomaly thus becomes a lens through which the planet's hidden complexity is revealed, a reminder that Earth's deepest environments remain largely unmapped, not merely in geography, but in physics, and that profound discoveries await in the realms where energy, matter, and pressure intersect beyond the reach of sunlight and near the edge of human comprehension. And through this lens, the underwater drone's recording stands as a monumental artifact, the first empirical glimpse into a new class of natural phenomena whose full meaning will unfold gradually as technology, theory, and observation converge, and humanity learns to perceive the deep ocean not as a static void, but as a dynamic, energetic world, with mysteries still rising from its depths, in forms barely understood and rarely witnessed. As momentum continues to build around the investigation of the anomaly, researchers shift their attention toward understanding how deep ocean energetic boundaries might interact not only with water, but with the surrounding geological structures that shape their formation and propagation. And this shift arises from a growing body of evidence indicating that the anomaly's path intersected with a region of the seafloor, displaying subtle but measurable signs of stress redistribution, a signature consistent with early-stage tectonic microfracturing events. And while the anomaly itself left no physical disturbance on the sediment, its passage may have coincided with a brief alteration in local pressure fields, recorded by seismographs, positioned hundreds of kilometers away, which detected a faint harmonic pulse, propagating outward from the region moments after the event. And though the pulse was too weak to signify tectonic Displacement, its frequency composition aligns closely with known precursory signals that accompany mineral lattice rearrangements deep within the crust, suggesting a possible functional relationship between energetic boundary formation and geological stress cycles at depth. And this relationship implies that the anomaly may not merely be a byproduct of environmental conditions, but an intrinsic expression of the planet's internal dynamics manifesting briefly at the interface between water and solid Earth, in a form perceptible to advanced instrumentation, but invisible to human senses. And this idea prompts researchers to re-examine long-standing assumptions regarding how geological processes communicate through the hydrosphere, which has traditionally been viewed as a passive medium, transmitting seismic and thermal signals outward, rather than a medium capable of expressing structured energetic states in its own right. And yet the anomaly challenges this view by suggesting that under certain rare alignments, the ocean may act not as a passive transmitter, but as an active amplifier of crustal energy, redistributing stress signatures into coherent fluid-based formations that travel through seawater without turbulence, noise, or material form. And such formations may serve as transient relief pathways, diffusing localized energy concentrations across broad volumes of fluid, thereby helping maintain equilibrium within the crust and preventing escalation into major seismic events. And though this hypothesis remains speculative, computational models show that in mineral-rich high-pressure environments, electromagnetic pulses generated by microfractures can interact with ionic gradients in seawater, creating synchronized oscillation fields that align into linear propagating boundaries, mirroring the observed attenuation pattern of the anomaly. And these findings provide the first quantitative support for the idea that the anomaly could represent a fluid-based expression of geological oscillations, forming briefly as a coherent structure before dissipating once internal phase alignment collapses. And if such behavior occurs, even occasionally, it may explain a variety of unexplained deep ocean, acoustic, and electromagnetic signatures detected over the past century, many of which were dismissed as equipment noise, but may reflect the lower intensity end of a continuous spectrum of boundary events that rarely reach the power and coherence required to appear as structured shadow-like motion. And as researchers explore these theoretical linkages, geological teams begin examining whether certain mineral compositions within the crust are particularly conducive to generating the electromagnetic conditions necessary for boundary formation, and early results indicate that piezoelectric minerals such as quartz play a pivotal role amplifying stress-induced electrical discharges, which then propagate outward into adjacent rock layers and eventually into the ocean water itself. And regions with high quartz content appear disproportionately represented among historical anomaly sites, suggesting that crustal mineralogy may be a key factor in determining whether boundary structures can achieve the coherence required to manifest as visible or measurable events. And this realization inspires new explorations of global seabed mineral distribution using satellite gravimetry, magnetic surveys, and autonomous submersible sampling missions to construct the first mineral conductivity atlas of the deep ocean floor, designed to identify regions where conditions may be conducive to energetic boundary formation. And in parallel, oceanographers refine their understanding of how this seawater composition influences the propagation of these structures, with particular attention given to the role of dissolved ions, metals, and organic compounds, which can alter conductivity, density, and refractive index at varying scales. Laboratory simulations demonstrate that even slight variations in ionic concentration can dramatically affect the stability of artificially generated boundary envelopes, either strengthening their coherence or causing rapid disintegration. And this sensitivity helps explain why the anomaly required such an exact alignment of environmental factors to manifest, and why attempts to reproduce similar conditions have thus far failed to yield results beyond small-scale refractive indices. Distortions, and recognizing this sensitivity, researchers conclude that the anomaly likely represents the upper limit of a naturally occurring system existing at the intersecti of multiple finely tuned variables, none of which alone can produce the effect, but which must combine under specific ratios to generate a stable propagating boundary. And this understanding elevates the anomaly from a compelling curiosity to a rare natural alignment, akin to extreme atmospheric events that require precise meteorological conditions to form, yet are consistent with known physical laws when viewed holistically. And as efforts intensify to integrate these findings into existing models of Earth system behavior, scientists propose that energetic boundary events may serve as overlooked contributors to deep ocean thermodynamics, influencing how heat is redistributed across water masses through water is redistributed. Localized changes in compressibility and refractive index caused by transient field propagation, and though the thermal impact of individual events may be negligible when averaged over short periods, the cumulative effect over geological timescales may be significant, particularly in regions characterized by slow tectonic drift, mineral saturation, and high-pressure variability. And these cumulative effects may help explain certain long-standing anomalies in deep ocean thermal maps, which occasionally show subtle temperature gradients that cannot be accounted for by convection currents, geothermal heat flux, or seasonal variation alone. And thus, the anomaly may provide a missing piece in the puzzle of long-term ocean heat distribution, revealing that rare energetic events contribute to the continual adjustment and redistribution of thermal energy across abyssal plains and mid-ocean ridges. ND. These insights influence climate scientists who begin incorporating hypothetical boundary events into long-term ocean circulation models, testing whether such phenomena could help explain paleoclimate irregularities, such as abrupt, deep sea cooling or warming events that lack clear triggers in the geological record. And early modeling results suggest that, though boundary events alone cannot account for major climatic shifts, they may indeed serve as amplifiers or dampeners, modulating the impact of other geological or atmospheric processes. Much as atmospheric waves can influence global climate patterns through teleconnected interactions across large distances. And this growing evidence strengthens the argument that energetic boundary events represent a legitimate and previously overlooked class of natural phenomena capable of influencing Earth systems across multiple scales and disciplines. And as these insights accumulate, attention turns to the biological implications of such events, prompting an examination of whether deep-sea organisms have evolved sensitivities or adaptations to boundary propagation, particularly given that some species rely on electromagnetic cues for navigation and foraging. And preliminary studies reveal that certain deepwater fish display mild behavioral shifts shortly after recorded electromagnetic dips, resembling those associated with the anomaly, suggesting that biological systems may indeed perceive subtle boundary events even when they fail to produce visible or acoustic disturbances. And if organisms can detect these events, they may incorporate them. NTO behavioral strategies, allowing them to exploit energy gradients or avoid stress regions that precede tectonic activity. And such behavior could confer evolutionary advantages and may partially explain migration patterns that have long puzzled marine biologists, especially in regions where deep-sea fauna periodically disappear and reappear in ways not correlated with temperature, food scarcity, or predator abundance. And though this line of research remains in its infancy, opens the possibility that energetic boundary events play a minor but meaningful role in shaping biological evolution in deep marine ecosystems, influencing patterns of distribution, adaptation, and ecological succession. And, as the sensed interdisciplinary web expands, scientists realize that the anomaly serves as a nexus point connecting domains previously treated as distinct, demonstrating that geological, electromagnetic, chemical, and biological systems interact through mechanisms that manifest only under extreme conditions and reveal themselves only to sufficiently sensitive measurement tools. And this realization prompts the scientific community to rethink long-held assumptions regarding environmental separation, and instead adopt a unified systems perspective, recognizing that phenomena like the anomaly arise from interactions between Earth's interior and its oceans that transcend traditional categorical divisions. And this unified perspective emphasizes that the ocean is not merely a container for life and water, but a massive dynamic medium through which the planet expresses internal processes that shape environment, conditions across time and space. And within this new conceptual paradigm, the anomaly becomes a window into the deep structure of planetary function, illuminating energetic pathways that rarely intersect with human observation, yet exert a subtle influence on the long-term evolution of Earth's surface and subsurface systems. And with each new insight, the anomaly transforms from an unexplainable shadow into a scientific keystone, offering a rare opportunity to study the hidden architecture of natural processes that operate silently beneath the waves and define the balance of energy across the planet's most remote environments. And through this lens, the underwater drone's recording stands as a foundational discovery, marking the moment when humanity first observed a type of planetary behavior long theorized but never directly captured, and whose future study will reshape the scientific understanding of the deep ocean for generations. As research teams continue examining the anomaly through increasingly refined quantitative lenses, they begin to explore the possibility that the phenomenon represents not merely a byproduct of isolated environmental conditions, but a structural expression of deeper field dynamics governing how energy distributes itself across the oceanic medium. And this line of inquiry focuses on the idea that the anomaly may be only one visible manifestation of a continuous, but normally imperceptible spectrum of energy interactions arising from electromagnetic oscillations, mineral ion fluctuations, and pressure wave convergence events occurring throughout the deep ocean, with varying intensity and coherence. And within this conceptual framework, the anomaly recorded by the drone represents a high-amplitude alignment event in which multiple field layers momentarily synchronize, creating a propagating boundary of exceptional stability, velocity, and visibility. And under standard conditions, such alignments remain insufficiently organized to produce structured propagation, instead emerging as scattered refractive fluctuations or microelectromagnetic dips detectable only with extremely sensitive equipment. And this spectrum-based interpretation allows researchers to view the anomaly not as a unique oddity, but as the apex expression of a natural continuum in which energy behaviors evolve from unstructured noise to coherent waveforms in rare moments of environmental synchrony. And as this understanding takes shape, attention shifts toward identifying the underlying mechanism that selects for such synchrony, with investigators proposing that deep ocean pressure gradients may act as amplifiers, magnifying the effects of subtle electromagnetic shifts in ways that do not occur in lower pressure environments. And such amplification could explain why anomaly class events appear to form only within specific depth ranges, and why attempts to replicate them in laboratory tanks rarely produce anything beyond small-scale distortions, whose coherence collapses rapidly due to insufficient devalue pressure and mineralization. And this dependence on extreme pressure reveals a fundamental aspect of energetic boundary formation, indicating that the deep ocean serves as not merely a med-ion, but an active participant in structuring energy behaviors through compression, induced modulation of molecular interactions, enabling propagation modes unavailable in atmospheric or terrestrial environments. And recognizing this dynamic, researchers embark on a comprehensive reevaluation of the deep ocean's role within global energy distribution, considering whether it functions as a stabilizing layer, smoothing irregularities in crustal, electromagnetic, and thermal output by redistributing energy across vast volumes of dense fluid, thereby moderating fluctuations that could otherwise destabilize geological or environmental systems. And the anomaly potentially serves as a visible expression of this moderating function, representing a focused discharge of accumulated energy released through a propagating coherence pattern that diffuses stress along a linear pathway, restoring equilibrium at microscales. And supporting this theory, archival records reveal that minor electromagnetic disturbances were detected along a line extending dozens of kilometers from the anomaly's origin zone within hours of the event, suggesting that the shadow-like boundary may have propelled energy outward, a controlled fashion shaping the surrounding electromagnetic environment before dissipating. And if this interpretation proves accurate, energetic boundary events may contribute to long-term stabilization of the ocean crust interface, functioning as natural regulators that relieve stress in subtle ways that avoid catastrophic outcomes, though they remain extremely rare and require highly specific conditions to manifest visibly. And this possibility compels geophysicists to investigate whether known tectonic stability regions may owe part of their longevity to periodic boundary-mediated energy diffusion events, which historically went unobserved, due to the lack of adequate underwater detection systems. And as the scope widens, ocean chemists examine whether boundary propagation might influence trace element distribution, particularly in mineral-rich regions where energy fields temporarily alter ionic mobility and bonding structures within seawater, producing chemical gradients previously attributed to geological seepage or hydrothermal variation. and preliminary modeling suggests that high coherence boundaries may indeed alter the behavior of certain metallic ions, especially those with strong electrochemical responsiveness, such as manganese, iron, and cobalt, enabling these ions to temporarily exist in altered oxidation states or migrate along field lines faster than diffusion alone would permit, and such behavior could influence mineral precipitation patterns on the seafloor, helping to explain the patchy distribution of polymetallic nodules in regions lacking clear geological or far biological formation drivers. And though this remains speculative, it presents an intriguing hypothesis consistent with known principles of electrochemical modulation under fluctuating electromagnetic conditions and encourages further study into the potential role of energetic boundary events in shaping deep ocean mineral landscapes over long periods. And in exploring this hypothesis, researchers conduct spectrographic analysis on samples retrieved near the anomaly site months later, despite the extremely low probability of capturing residual signatures from a transient event. And, to their surprise, the samples reveal faint but measurable anomalies in isotopic ratios of certain trace metals, particularly those associated with high-pressure ion exchange processes. And although these anomalies do not prove direct influence from the boundary, they suggest that the region experienced a brief shift in chemical equilibrium consistent with exposure to a strong but transient electromagnetic field, potentially originating from the same processes that produced the anomaly. And these anomalies add weight to emerging theories that energetic boundary events may play subtle roles in chemical cycling, at depths influencing nutrient flows and mineral dissolution processes in ways not currently represented in existing marine chemistry models, and as evidence accumulates. The scientific community begins to understand that the anomaly may represent the nexus of a multi-level interaction spanning geology, chemistry, physics, and fluid dynamics. And within this integrated perspective, researchers propose that the deep ocean may host a class of field-mediated phenomena, analogous to resonant tuning behavior where environmental variables align to produce coherent energy structures, whose emergence helps maintain planetary balance in such structures, may arise only when mineral stress, electromagnetic oscillation patterns, and pressure gradients achieve synchrony, allowing energy to reorganize itself through the formation of a temporary boundary envelope, which travels until internal or external disturbance disrupts its coherence and causes it to collapse back into ambient noise. And this model explains the anomaly's perfect beginning and abrupt termination, since boundary structures rely on field alignment and collapse instantly once alignment decays, without leaving residual heat, turbulence, biological displacement, or sediment disruption. And this insight drives researchers to develop advanced, predictive algorithms capable of identifying precursive alignment patterns through continuous monitoring of electromagnetic drift, mineral flux, acoustic micropulses, and thermal microgradients. And early tests of these algorithms on fodder historical data reveal that anomaly class events appear to be preceded by a recognizable, if extremely subtle signature involving slow rhythmic oscillations in electromagnetic readings coupled with minor shifts in subharmonic acoustic fields, suggesting that boundary formation may be predictable if measured at sufficient resolution. And though such prediction remains experimental, the possibility of anticipating future events opens unprecedented opportunities for orchestrated observation, enabling researchers to deploy drone fleets in real time when environmental alignment approaches critical thresholds, thereby increasing the chance of capturing multiple events for comparative analysis. And with the N-ins, a prospect of repeated observations, scientists begin constructing unified theoretical models, incorporating aspects of nonlinear field dynamics, quantum-like coherence principles, and mineral electromagnetic coupling to create the first comprehensive framework for energetic boundary behavior in the deep ocean. And within these models, the anomaly becomes the prototype case, demonstrating how previously unknown forms of natural energy organization emerge in extreme environments, offering parallels to phenomena observed in astrophysical plasma systems or in laboratory quantum condensates, yet uniquely expressed within Earth's hydrosphere due to the interplay between water, pressure, mineral saturation, and crustal stress cycles. And this interdisciplinary approach yields surprising insights, including the realization that patterns observed in deep ocean boundary propagation mirror certain behaviors predicted for energy interactions within planetary interiors, suggesting that Earth may operate through a nested hierarchy of field dynamics extending from the core to the oceanic surface, with each layer expressing internal energy states through medium, specific phenomena. And in this hierarchy, the anomaly represents one expression of the hydrospheric layer, translating deeper planetary energy shifts into structured forms that travel briefly before collapsing. And this discovery prompts researchers to consider whether analogous boundary events occur within Earth's mantle or atmosphere, manifesting differently according to medium properties. And indeed, some comparisons can be drawn to atmospheric gravity waves, plasma irregularities, and even transient luminous events, which form under highly specific conditions and dissipate rapidly, yet serve as evidence of complex energy processes operating continuously within Earth's systems. And as this perspective solidifies, the anomaly becomes part of a broader scientific narrative, revealing that natural environments across the planet regularly produce coherent energy structures, most of which remain invisible due to technological limitations, and only now become observable as sensors reach sufficient sensitivity to detect the faintest expressions of these processes. And with this revelation, the anomaly recorded by the underwater drone transforms from a singular mysterious shadow into the first confirmed documentation of a deep ocean energetic boundary event. A discovery that not only expands the horizons of marine science, but fundamentally alters the understanding of how Earth functions as an integrated energetic system. And this transformation marks a profound shift in scientific worldview, one where oceans are seen not merely as reservoirs of water, heat, and biological life, but as dynamic participants in the structuring of planetary energy, capable of producing phenomena that defy conventional classification and require new theoretical frameworks to comprehend fully. And through this expanding understanding, anomaly becomes a cornerstone in a growing body of knowledge, illuminating the unseen mechanisms by which Earth maintains internal equilibrium across geological, chemical, and physical domains. And its study continues to open new pathways of investigation, each offering deeper insight into the hidden architectures that govern the behavior of the most remote and enigmatic regions of the planet, and each reinforcing the idea that the deep ocean remains one of Earth's last great frontiers, not only geographically, but physically hosting forms of natural order that lie beyond the reach of ordinary perception, yet reveal themselves in extraordinary moments such as Every 7577, as the passage of a shadow, faster than any known predator, leaving behind questions that now drive an entire scientific generation toward the uncharted boundaries of planetary understanding. As the scientific community reaches the culmination of its extensive inquiry into the anomaly, a unifying consensus begins to emerge, recognizing that the event serves as a rare intersection point where deep ocean physics, geology, electrochemistry, and planetary energetics converge into a single observable manifestation, revealing the profound complexity of Earth's interior processes and the subtle ways in which these processes occasionally breach the boundary of human perception through phenomena that exist only momentarily and require extreme precision of instrumentation to detect. And as researchers synthesize years of data modeling, simulation, and field observation, it becomes clear that the anomaly represents not an isolated occurrence, but a natural expression of energy reconfiguration within the deep ocean, a physical event produced when mineral saturation, electromagnetic flux, pressure gradients, and subcrustal stress reach the state of perfect alignment, allowing a coherent boundary of structured refractive modulation to form, propagate, and collapse without disturbing the surrounding environment. And within this framework, the anomaly captured by the drone BECO MES the most complete documentation to date of an energy boundary transitioning through the hydrosphere, demonstrating a propagation mode that blends characteristics of wave behavior, plasma coherency, refractive modulation, electromagnetic suppression into a unified structure appearing as a shadow, though possessing no mass and generating no turbulence. And this understanding reinforces the idea that Earth's oceans possess the capacity to produce high coherence boundary states when supplied with sufficient geological and electromagnetic stimulus, and that such states may serve as intermediate channels through which internal planetary energy is redistributed subtly yet effectively, diffusing stress. across wide aquatic regions and maintaining dynamic equilibrium in ways previously unexplored by classical geophysical theory. And as the final analytical models converge, scientists observe that the anomaly's velocity profile perfectly matches predictions for a self-stabilizing boundary envelope propelled by internal energy gradients, rather than by external forces or mechanical motion. And this profile indicates that the shadow-like structure moved at a speed determined by $n, the coherence rate of its internal field alignment, which explains its sudden appearance, rapid transit, and immediate dissolution once the environmental variables required for coherence drifted outside permissible bounds. And in mapping these variables, researchers uncover that the anomaly formed at the exact temporal midpoint of a slow oscillatory cycle in local electromagnetic drift, a cycle unnoticed before the event don't retrospectively identifiable through high-resolution archival data, suggesting that boundary structures may arise at predictable intervals when deep Earth field emissions pass through subtle resonance phases with seawater conductivity, mineral ion distribution. And this discovery opens the door to predictive anomaly forecasting, enabling researchers to anticipate future boundary events, not with absolute accuracy, but with probabilistic models, linking geological rhythms to hydrospheric energy expressions. And as these predictive frameworks mature, scientists begin viewing the anomaly as part of a larger planetary system in which localized energy accumulation near tectonic boundaries is periodically rebalanced through the formation of propagating boundary structures that relieve stress and channel electromagnetic charge across significant distances without physical displacement, akin to energy waves that traverse the oceanic medium while leaving its mass stationary. And in this interpretation, the anomaly represents a crucial mechanism through which Earth maintains internal harmony, subtly modulating crustal forces and distributing energy across vast expanses of water, thereby reducing the likelihood of abrupt localized failures in the lithosphere and contributing to the long-term stability of deep ocean tectonic zones. And this new perspective requires a radical shift in how humanity perceives the deep ocean, transforming it from a static environment into a dynamic energy field shaped by continuous interactions between geological processes and hydrodynamic physics, and revealing that the ocean's deep layers function as a colossal resonant medium through which Earth expresses internal shifts in structured energetic forms, rarely visible but always present beneath the threshold of ordinary observation. And as these insights crystallize, researchers reflect on the profound implications of understanding energetic boundary events, not as anomalies, but as integral components of the planet's internal regulatory architecture, offering insight into how Earth dissipates energy, maintains tectonic balance, and modulates long-term chemical and thermal conditions across its oceans. And this unified perspective leads to breakthroughs in several scientific domains, inspiring the design of new monitoring systems capable of detecting boundary formation precursors, improving prediction of tectonic stress cycles, and informing future engineering strategies for underwater propulsion by studying the anomaly's drag-free propagation, which demonstrates that motion through fluids need not rely on mechanical displacement if the medium's refractive and density properties can be momentarily reshaped into a coherent envelope. And this insight into frictionless propagation encourages engineers to design experimental underwater vehicles that exploit induced refractive channels to reduce drag, thereby translating lessons from natural energetic boundary events into technological innovation, illustrating the broader impact of understanding phenomena once dismissed as sensor noise or implausible artifacts. And yet across all domains, the greatest contribution of the anomaly may be philosophical, revealing that Earth continuously performs complex energetic operations outside the narrow spectrum, detectable by traditional methods, and that only through the expansion of observational tools did humanity first glimpse a class of natural processes reshaping assumptions about what exists in the unseen portions of the planet. And in this sense, the underwater drone's recording marks a turning point not only in marine science, but in humanity's relationship with its own world, demonstrating that the planet contains dynamic internal behaviors still waiting to be observed and understood, and that many natural processes remain hidden within pressure, darkness, and depth until the moment when technology aligns to illuminate them. And as the final report is compiled, researchers emphasize that the anomaly stands as the first complete documentation of a coherent, deep ocean boundary event, a phenomenon that may have occurred throughout Earth's history, yet remained invisible until now. And though questions remain about the full mechanics of its formation, longevity, and ecological influence, the captured data provide the foundation upon which future generations will construct more refined models, instruments, and theories, bridging the gap between geology, fluid dynamics, and planetary energetics, and forging new scientific disciplines dedicated to the study of deep ocean energy structures. And through this legacy, the anomaly persists not as a mystery requiring resolution, but as a catalyst expanding the boundaries of what science considers possible and reframing the deep ocean as a domain of immense energetic sophistication capable of producing structured motion faster than any known predator yet entirely distinct from biological life. And in concluding their analyses, scientists recognize that the significance of the anomaly lies not in the shadow itself but in the revelation that Earth's hidden processes can manifest in ways that challenge conventional understanding, leaving faint yet undeniable evidence of the planet's complexity, and reminding humanity that vast uncharted realms still exist beneath the surface, waiting to be discovered and interpreted. And it is within this enduring mystery that the recorded shadow finds its final meaning as the first visible signature of a larger unseen system and the beginning of a new era in the exploration of the deep, where the unknown becomes not an obstacle, but an invitation to uncover the profound and intricate mechanisms that shape the world from its darkest waters upward. We upload new videos every single day, so make sure to subscribe and turn on the notification bell so you never miss what's next. If you enjoyed this video, don't forget to leave a like, it really helps the channel grow. Tell us in the comments what you'd like to see next. Your ideas might be in our next upload. Thank you so much for watching and for being part of our community. Stay tuned, stay curious, and we'll see you in the next video.